Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. Today, I am going to start the fifth chapter of the Engineering Electromagnetics book, and the title of this chapter is Conductors, Dielectrics, and Capacitance. So, in this chapter, first of all, I will discuss the current and current density. From the fifth chapter, we will be dealing with moving charges, and the study of moving charges is called electrodynamics. And whenever the charge is moving with the passage of time, we will say that the current is flowing. So the definition of current is time rate of change of charge. So I is equal to dq by dt. And here I will define a new term which is called current density. And current density is denoted by capital J, and it is also a vector quantity. So delta I can be expressed as Jn into delta S. So Jn is actually the component of current density normal to the crossing surface, right? So I is equal to J into delta S. So Jn means the component of current density which is perpendicular to the surface delta S. So that's why N is written over here. And we know that the unit vector of a surface is also perpendicular to the plane. So this can be written as J dot delta S. So there is a dot product, and the total current will be equal to J dot ds. So the surface integral of J dot ds will be equal to the total current. Now we can discuss a simple case in which we can see a volume charge distribution over here, and the volume charge density in this case is represented by rho v, and the total charge is equal to rho v into delta v. And we are assuming that with the passage of time, this volume charge is flowing along the x-axis. So after a time delta t, this volume charge distribution will be at this location. So this volume charge distribution has moved by a distance of delta x along the x-axis, and delta L is actually the total length of this volume charge distribution along the x-axis. So this is actually delta S, and this is x-axis, y-axis, and this is the z-axis. Again, delta q is equal to rho v delta v. This is delta S, and the propagation of this volume charge density is along the x-axis. So delta I is equal to delta q by delta t, and in the time delta t, the displacement that has been covered by this volume charge distribution is delta x. So this can be written as rho v into delta v divided by delta t. So delta q is equal to rho v delta v divided by delta t, and delta v, which is the incremental volume of this distribution, can be written as delta s multiplied by delta x. Delta s is the surface area of this plane, and delta x is actually the distance incremental displacement at which this volume charge distribution has moved in time delta t. So this thing can be written as rho v delta s into delta x by delta t. Delta x by delta t is actually the velocity of this charge distribution along the x-axis. So this is vx, and delta I is equal to rho v delta s into vx. And if we take this delta s towards the left hand side, it will become delta I over delta s equal to rho v into vx. So this will become j. So j is equal to rho v into v. So this expression is actually telling that a charge rho v moving with velocity v constitute a current j. So current is j, current density, v is the velocity, and rho v is the volume charge distribution. So if we have charge rho v and it is moving with a velocity v, then there will be a current flowing. If either rho v is zero, it means current is zero, and if there is a charge but its velocity is zero, it means this is a static charge, and in that case again the current density will be equal to zero. So let's solve a simple example. In this example, we are given the current density as 10 rho square z a rho minus 4 rho cos square phi a phi. So we have to calculate the current density at this point. So let's substitute these three components in this expression, and then we will get the value of current density, which is 180 a rho minus 3 a phi ampere per meter square. And now we have to calculate the total current due to this volume charge distribution, and we know that I is equal to j dot ds. and we are given this surface, right? Rho is equal to 3, phi varies from 0 to 2 pi, and z varies from 2 to 2.8. So let's evaluate the surface integral, and ds in this case will be equal to rho d phi dz a rho. So I will be equal to j dot ds, and j dot ds will be equal to j dot rho d phi dz a rho. So a rho dot a rho will be 1, and a phi dot a rho will be equal to 0. So only this component along the rho axis will be considered. So 10 rho square z rho d phi dz, and we can evaluate the surface integral, and it will become 10 rho cube z d phi dz. So this is 10 rho cube, and rho is constant as 3, and the integral of z will be equal to z square by 2, and the integral of d phi is phi. So the limit of phi is from 0 to 2 pi, so it will become 2 pi, and this is z square over 2. So let's put the limits of z from 2 to 2.8. So after these calculations, finally we will get 3.257 into 10 raised to power 3 amperes, which is the total current. Next topic is the continuity of current, and the continuity of current can be defined as charge can neither be created nor be destroyed, but equal amount of opposite charges may be simultaneously created. So in this case, we can assume a volume charge distribution, and this volume charge distribution constitute a closed surface, and out of this surface, we will assume that these point charges are undergoing scattering in all the directions. So after some time, the net amount of charge will be decreased because these point charges are scattering out of this closed surface, and the total amount of charge will be decreasing with the passage of time. So since the charges are moving outward, so definitely there will be current flowing, and the current in that case will be equal to j dot ds. And we will use a closed surface integral in this case because this volume charge distribution constitutes a closed surface, and that current is also equal to minus dq by dt. And we have put a negative sign over here because the number of charges in this volume is decreasing with the passage of time. So let's apply divergence theorem for this expression. And according to divergence theorem, j dot ds closed surface integral is equal to del dot j dv volume integral. And this implies that this volume integral is equal to minus dq by dt. And dq can be written as rho v dv, right? So it will become minus d by dt rho v dv volume integral, and this can be written as del dot j dv equal to volume integral minus partial rho v over partial t dv. So if we compare these two sides of this expression, we will get del dot j equal to minus partial rho v over partial t. So this is the final expression, and that expression is the mathematical form of continuity of current. And the statement of continuity of current is the charge can neither be created nor be destroyed. Equal amount of opposite charges may be simultaneously created. And this expression can be stated as current diverging from a small volume per unit volume is equal to the time rate of decrease of charge per unit volume. So that is all about our today's lecture on current and continuity of current. So I hope you have understood the concepts discussed in this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.